China just spent more than $1 billion on something that sounds almost too boring to matter. Not transistors, not lithography machines, glass. Plain, ordinary glass. And yet, inside semiconductor labs in Beijing, Shenzhen, and Hefei, engineers are calling it the most important material shift in chip making in 3 decades. To understand why a sheet of glass has the power to rattle an industry worth over $600 billion a year, you have to forget everything you think you know about what a chip actually is. Most people imagine a chip as a single, self-contained brain, a tiny silicon square that does all the thinking. That picture stopped being accurate years ago. A modern AI chip, the kind that powers ChatGPT-style models or trains the next generation of artificial intelligence, isn't one piece of silicon. It's dozens of pieces, called chiplets, stitched together like a mosaic. And the thing holding that mosaic together, feeding it power, carrying its signals, keeping it flat and stable under extreme heat, is something almost nobody outside the industry has ever heard of. It's called the substrate. For more than 30 years, the substrate has been made of organic resin, essentially a high-tech fiberglass and epoxy sandwich, the same basic family of material that's been quietly sitting underneath every chip since the 1990s. It worked fine when chips were small and power-hungry processors were the exception, not the rule. But the AI boom changed the math completely. Today's AI accelerators are enormous. They pack more transistors, more chiplets, more high-bandwidth memory stacks into a single package than anyone designing organic substrates back in the 90s could have imagined. And organic material is starting to break down under that pressure. Literally. Here's the core problem nobody outside engineering circles talks about. When you manufacture a chip package, you have to heat it to extreme temperatures to bond all those layers together. Organic resin expands and contracts unevenly when it heats up. As packages get bigger, this uneven expansion causes warping. The substrate physically bends, sometimes by amounts invisible to the eye but catastrophic. At the microscopic scale these chips operate on, even a few microns of warp can break the delicate electrical connections between chiplets, killing yield, which is the percentage of working chips that come off the line. In an industry where a single advanced AI chip can cost tens of thousands of dollars, losing yield to warping isn't a minor inconvenience. It's a multi-billion-dollar problem. There's a second wall closing in too: wiring density. AI chips need to move staggering amounts of data between chiplets, and that requires extremely fine, extremely precise wiring etched into the substrate. Organic materials are reaching the physical limit of how fine that wiring can get. Push past a certain point, and the material's own dimensional instability, its tendency to shift slightly with humidity and temperature, starts introducing errors. And then there's heat itself. AI chips today can draw kilowatts of power, output enough heat to warm a small room, and organic substrates were never built with that kind of thermal load in mind. This is where glass enters the picture, and once you understand its properties, it stops sounding like a strange choice and starts sounding almost obvious. Glass is remarkably flat. It barely expands or contracts with temperature, which means none of that warping problem that plagues organic substrates. Engineers measure this property as the coefficient of thermal expansion, and glass's number happens to sit remarkably close to silicon's own number, which means a glass substrate expands and contracts almost in lockstep with the silicon chip sitting on top of it. That single property alone solves the warping crisis that's been quietly throttling the industry's ability to build bigger AI chips. But the advantages don't stop there. Glass can be manufactured astonishingly smooth. Researchers have measured surfaces roughly 5,000 times smoother than organic substrate material. That smoothness matters because when manufacturers deposit ultra-thin metal layers onto a substrate to create wiring, any roughness in the surface underneath can create defects in those layers. Fewer surface imperfections means fewer defective chips rolling off the line. Glass is also an excellent electrical insulator, which reduces a phenomenon called crosstalk, essentially electrical interference between densely packed wires, making it far better suited to the ultra-high-speed signaling that next-generation chips demand for things like 5G, 6G, and high-bandwidth AI interconnects. And then there's perhaps the most science fiction-sounding advantage of all. Glass can guide light. Because glass is naturally transparent and excellent at transmitting optical signals, chip designers are exploring building high-speed optical data pathways directly into the substrate itself instead of relying purely on electrical wiring. That could eventually mean chips that move data not just faster, but with dramatically less energy wasted as heat, a serious advantage when an AI data center's biggest hidden cost is its electricity bill. Today, when two chiplets need to talk to each other across a package, that conversation happens over copper wiring, and copper has real physical limits. It resists the flow of electricity, it generates heat as a byproduct, and the longer the wire, the worse those problems get. Light doesn't have that problem in the same way. A signal carried as light through a glass pathway can travel further, faster, and with far less energy loss than the same signal pushed through copper. That's the same basic principle behind fiber optic internet cables replacing old copper telephone lines decades ago, just shrunk down to the scale of a chip package. If engineers can get optical interconnects working reliably inside the substrate itself, it could remove one of the biggest hidden energy costs in modern AI computing, at a moment when data centers are already straining regional power grids just to keep up with demand. Put all of that together, and you get a substrate that can support far denser, far larger chip packages than organic ever could. To put a number on it, researchers have already demonstrated mounting 60 individual chips onto a single glass substrate, a scale that would be essentially unworkable using today's organic materials. As AI hardware races toward what engineers are now calling kilowatt-class processors, chips that draw as much power as a household appliance, that headroom isn't a luxury, it's becoming a requirement. Now here's where China comes into the story, and why this particular moment, early in 2026, is being treated as such a turning point. China has just officially declared 2026 the first year of large-scale glass substrate production inside the country. That's not marketing language pulled from a press release. It's a deliberate strategic positioning statement, and it matters because of where China is starting from. China didn't build this capability from a semiconductor lab, it built it from its display industry. For 2 decades, Chinese manufacturers have been mass-producing glass for LCD and OLED television and smartphone screens at a scale and cost efficiency that essentially no other country on Earth can match. That gave China something unusual. An enormous, mature, battle-tested industrial base for precision glass manufacturing sitting right there, ready to be redirected toward a completely different application. Instead of starting a glass substrate industry from zero, Chinese companies are repurposing decades of display glass expertise and pointing it at chip packaging. The company leading that charge is BOE Technology, the world's largest LCD manufacturer, a name most people have never heard of, despite the fact that BOE glass is probably inside the television or monitor you're using right now. BOE has poured significant research and development resources into a dedicated semiconductor glass division, and by early 2026, the company had already moved beyond small, experimental pilot lines toward production scale manufacturing of standardized glass core substrates engineered specifically for high strength and minimal warpage, with mass production aimed squarely at AI chips. Industry watchers expect full commercial scale output sometime after 2026, but the infrastructure being built right now is the clearest signal yet that this isn't a side project. It's a core strategic bet. BOE isn't alone. Visionox, another major Chinese display manufacturer, announced it's pouring roughly 5 billion renminbi, somewhere in the neighborhood of $700 million, into an expansion plan that explicitly includes glass substrate development alongside related work in X-ray technology. To support that ambition, Visionox has spent months building out its own materials and equipment supply chain rather than relying on imported machinery. Then there's AKM, Meadville, a printed circuit board manufacturer, also preparing to enter the glass substrate supply business, and Hans Laser, a domestic equipment maker that's begun delivering Chinese-built laser drilling machines specifically designed to bore the ultrafine holes known as through-glass vias. That let electrical signals pass through a glass substrate from one side to the other. That's a critical detail, because drilling thousands of microscopic, perfectly aligned holes through brittle glass without cracking it is one of the hardest manufacturing problems in this entire field. Having a domestic supplier for that equipment means China isn't dependent on importing it. Perhaps the most eye-catching development, though, comes from JCET Group, China's largest provider of chip assembly and testing services. Essentially, the company that takes finished silicon and packages it into something that can actually be sold and installed in a server. In late 2025, JCET announced it had successfully integrated glass core substrates into its 1.6 terabit optical modules and into what's called co-packaged optics, a cutting-edge approach that places optical networking components directly alongside chip logic to speed up data movement between processors and massive AI data centers. That puts JCET in direct head-to-head competition with TSMC's CoWoS packaging technology, the same packaging approach TSMC uses to assemble NVIDIA's most advanced AI chips. If JCET can offer comparable or better performance using a glass-based alternative, it represents a real foothold in a part of the supply chain that has, until now, been almost entirely dominated by Taiwan. To understand why that matters so much, you have to understand just how much power has quietly concentrated in advanced packaging over the last few years. For most of semiconductor history, the real value sat almost entirely in the chip design and the fabrication process. Who could draw the smartest circuit and who could etch it at the smallest size? Packaging was treated as the boring, low-margin final step, something you did after the real engineering was finished. The rise of chiplets flipped that completely. Once a chip stopped being one piece of silicon and became dozens of smaller pieces that had to be stitched together, the company that controlled the stitching suddenly controlled a huge amount of the final product's performance, cost, and yield. TSMC understood that shift early, and its CoWoS packaging line became one of the tightest bottlenecks in the entire AI industry. So tight that for nearly 2 years, the limiting factor on how many advanced AI chips NVIDIA could actually ship to customers wasn't silicon production at all. It was how many chips TSMC could package. A credible alternative to that bottleneck, even a partial one, is something every chip designer on the planet has an incentive to want to exist. It's worth pausing here to be honest about something the breathless headlines tend to skip over. China is not alone in this race, and it isn't even clearly ahead. Intel has been working on glass core substrates since at least 2023, filing aggressive patents and pouring research dollars into the technology years before China's recent announcements. In January 2026, Intel actually beat China to a public milestone, unveiling the first working sample that combines its own advanced EMIB packaging technology with a glass core substrate, demonstrated at a trade show in Japan. Samsung is exploring glass for its own AI and high-performance computing packaging, hoping to use it as a way to close the gap with TSMC. Corning, the American glass manufacturer best known for Gorilla Glass on smartphone screens, is positioning itself as a leading supplier of the ultra-high purity glass these applications require. German specialty glass maker Schott is doing similar work, and so is Japan's Nippon Electric Glass. The United States government, for its part, isn't sitting this one out either. Under the CHIPS Act, a company called Ipsolix received a preliminary award of $75 million to build what's described as a first-of-its-kind glass substrate manufacturing facility in Georgia. A direct attempt to anchor this entire emerging supply chain inside American borders before China, or anyone else, can lock in a decisive lead. And then there's the most telling data point of all. TSMC, the company that actually dominates advanced chip packaging today and manufactures the overwhelming majority of the world's most advanced AI processors, is moving on glass substrates more cautiously than almost anyone else in the industry. That might sound strange. Shouldn't the market leader want to move fastest? But there's a logical reason behind the hesitation. TSMC's entire packaging business is built around predictable, proven yield. Its current organic substrate-based CoWoS process, despite its limitations, is a known quantity that the company can manufacture reliably at enormous scale for customers like NVIDIA and Apple who need consistent supply, not experimental risk. Glass substrates, for all their theoretical advantages, still come with real unsolved manufacturing challenges. Cost-effective high-volume processing techniques are still being refined, and the broader packaging ecosystem still needs to adapt to handle a fundamentally different, more brittle material. TSMC appears to be watching the field test the technology before committing its own enormous manufacturing capacity to it. Some analysts call this caution. Others call it TSMC quietly working on its own glass roadmap behind closed doors while letting competitors absorb the early risk. So where does that leave China's position in all this? It's genuinely significant, but it's not the silicon-ending, world-shaking event that aggressive video titles want you to believe. What China actually has going for it is scale and existing infrastructure. Because Chinese companies already operate some of the largest, most cost-efficient glass manufacturing facilities on the planet, built over 20 years of dominating the global display panel industry, they have a real shot at undercutting competitors on cost once glass substrate manufacturing matures into true mass production. That's not a small advantage. In an industry where margins are thin and volume is everything, being the lowest cost producer at scale has historically been enough to reshape entire global supply chains, just as China did with solar panels and electric vehicle batteries. There's also a deeper strategic logic running underneath all of this that's worth understanding, because it connects to a separate but related story that's been circulating alongside the glass substrate news, sometimes blurred together with it in ways that cause confusion. Around the same time China was announcing its glass substrate ambitions, a Chinese government minister revealed that domestic manufacturers had successfully developed glass containers specifically engineered to hold photoresist chemicals, the light-sensitive materials used in the photolithography process that actually etches circuit patterns onto silicon wafers. This sounds almost trivially small compared to substrates and chiplets, but it matters enormously because photoresist is an extremely sensitive, easily contaminated chemical, and for years, the specialized glass containers needed to store and transport it safely have come almost exclusively from Japan. By developing its own domestic alternative, China removed one more point of leverage that Japan, acting in coordination with broader Western export restrictions, had been able to use to constrain China's semiconductor ambitions. What's genuinely interesting is where that breakthrough actually came from. It wasn't a dedicated semiconductor research program at all. It traces back to the COVID-19 pandemic, when global demand for vaccines forced Chinese manufacturers to rapidly master the production of neutral borosilicate glass for vaccine vials, a material that has to be extraordinarily chemically stable, capable of withstanding high temperatures, and free of internal stress that could cause cracking. Well, it turns out those exact same properties, high melting point, precise viscosity control, chemical inertness, stress-free annealing, are essentially identical to what's needed for photoresist containers used in advanced chip fabrication. China didn't set out to build a semiconductor glass capability. It built one almost by accident, as a side effect of pandemic-era vaccine production, and is now redirecting that accidental expertise toward chip making. That pattern is worth sitting with for a moment because it reveals something about how China's industrial strategy actually tends to work in practice, as opposed to how it's often portrayed in dramatic headlines. Progress isn't always happening at the flashy, visible frontier, the next big GPU announcement, the next leaked benchmark. Often it's happening quietly, at overlooked structural choke points that most people never think about. A glass bottle here, a laser drilling machine there, a chemical container. Nobody outside a clean room has ever heard of. Individually, none of these breakthroughs sound dramatic. A glass bottle for chemicals doesn't make headlines the way a new graphics processor does, but stacked together over years, these unglamorous wins are how an entire industrial supply chain gradually becomes self-sufficient, not through one explosive headline moment, but through dozens of quiet ones that nobody outside the industry was watching. So is China's glass chip breakthrough really shaking the entire tech world the way the title promised? The honest answer is more nuanced than that, and more interesting too. China hasn't invented a revolutionary new material that the rest of the world doesn't have access to. Glass substrate technology is being pursued simultaneously by Intel, Samsung, Corning, Schott, and government-backed efforts in the United States. What China has done is commit decisively and at enormous scale to converting its existing dominance in display glass manufacturing into a serious play for a critical, emerging layer of the semiconductor supply chain. Right at the moment, the entire industry is being forced to abandon 30 years of organic substrate orthodoxy because AI chips have simply outgrown it. If China's bet pays off, and Chinese companies like BOE, Visionox, and JSET manage to close the remaining technical gaps in mass-producing reliable, high-yield glass substrates before competitors fully scale up, the country could end up controlling a meaningful slice of a technology that sits underneath essentially every advanced AI chip built from this point forward, regardless of whether that chip's logic comes from NVIDIA, AMD, or a Chinese chipmaker like Huawei. That would be a genuinely significant shift in global technological power, not because China built a faster chip, but because it positioned itself inside the foundation that every advanced chip from every country will eventually need to stand on. But that outcome is still very much in progress, not yet decided. The companies racing toward glass substrates worldwide are still working through real, unresolved manufacturing challenges, keeping brittle glass from cracking during high-speed processing, scaling laser drilling to the speed and precision mass production demands, and building an entirely new packaging ecosystem capable of handling a material the industry has never worked with at this scale before. Whoever solves those problems first and cheapest, at the highest reliable yield, is going to come out ahead. Right now, that race includes American, Korean, Japanese, German, and Chinese companies, all running roughly in parallel, each leaning on a different inherited strength. Intel's packaging research, Corning's materials science, Japan's precision equipment manufacturing, and China's sheer manufacturing scale built on 2 decades of making the screen in your pocket. What's genuinely true and worth taking seriously underneath all the hype is this. The substrate, the unglamorous foundation that chips sit on, has quietly become one of the most strategically important battlegrounds in the entire AI hardware race. For 30 years, almost nobody outside the industry paid it any attention. Now it's the thing that could determine which countries and which companies end up controlling the next generation of artificial intelligence hardware. And whether the breakthrough that ultimately wins this race comes out of a lab in Hsinchu, a fab in Oregon, or a converted LCD factory in Hefei, the material underneath the world's most powerful computer chips might very soon be the same material sitting in your kitchen window. That's really the story underneath the headline. Not a single dramatic chip that suddenly made silicon obsolete overnight, because nothing in this industry actually works that way. Real shifts in semiconductor manufacturing take years, sometimes decades, of unglamorous engineering, failed pilot lines, and incremental yield improvements before they ever show up in a finished product that you can buy. What's happening with glass substrates right now is the early, messy, competitive middle of exactly that kind of shift. And China has just made clear it intends to be one of the players writing how it ends, using an industrial advantage built quietly over 20 years in an entirely different business. Whether that bet pays off depends less on any single headline-grabbing announcement and more on which company and which country can solve the boring problems first, cracking less glass, drilling cleaner holes, and doing it all cheaper than everyone else at a scale the rest of the world simply cannot match.